So let me share. All right, we're gonna take a look at introducing graphing techniques, which is the second lab exercise. By the way, the next week, let's get the syllabus here. Next week, we're going to do lab techniques. So we're actually going to be in the lab, right? So you need your lab coat. If you don't want to use one of our scratchy pairs of glasses, bring your own. Be sure that your legs are covered and your feet are not open-toed shoes.
Do they have to be rubber or can they be cloth?
Cloth. Oh, they'd be cloth. Yeah, they'd be all right. We just need a barrier between your skin and anything you drop on it.
Don't matter as long as our feet are covered.
Yeah, your feet are covered.
All right.
Yeah. And that just gives you time. If you spill something on yourself, like your lab coat or your glasses or your feet, if you spill something on it, it gives you enough time, a buffer, so you can get that stuff off of you, or you can get to the shower. Right? It's a time management thing during an accident. So I did hand that one out, didn't I? Did I hand that one out? Okay, good. So come prepared, right? That's #1 safety rule. Be prepared before you walk into the lab. And actually think about things that could go wrong. Right? Think about something, say your lab partners got their they've got their hard copy of their paper method, and they just happen to be looking at it, and they walk over here and there's a Bunsen burner lit right underneath it. Right? So the thing goes, right, what do you do? Okay, so let's look at let me share graphing techniques. There we go. That's kind of small, but you've got your copies too, don't you? Everybody got their copy open? Okay, good.
Another copy of that.
Sure.
I forgot to graph it.
Yeah, I've got copies. I'm pretty sure I do. Lab technique, graphing techniques. Anybody else? No? Everybody got it? Okay. All right. So every lab is supposed to have at least one central theme, something that you're trying to demonstrate, something you're trying to prove, maybe. In this particular lab, what we're trying to make a point of is that it's all based upon human nature. Right? Humans are visual creatures. Right? We look at our world and we understand it based upon the picture that we get. And presenting the results of an experiment are no different. What you're trying to do, if you publish a paper in a journal, for instance, or if you circulate results of an experiment that you're conducting for your company, what you want to do is convince your peers, and especially your boss, that what you're doing is worth getting paid for. So one way to do that is to present your results in a picture form, in a graphical form, so that it's easier to make your point. And that's where we're headed today. We want to take our data, which you can present in like a massive table, just a series of numbers, but you put your audience to sleep, or they'll just throw your paper in the trash. Right? Can't understand what you're trying to say. If it's a small data set, just a few numbers, then maybe you can get away with it. But if you can draw a picture and base your argument upon what they see in that graph, then you're more likely to make your point. So that's where we're headed, and we're gonna work on the very simplest form of graphing. Right? Has everybody had algebra? Are you in algebra now? Are you in a math class? Okay. Have you done the Cartesian system? No. Okay. Cartesian. Or am I using a name that you're not familiar with? Cartesian coordinate system.
Is that like XY?
XY, yeah.
Okay.
Yeah.
Yeah.
Okay.
Yeah. Right. And you can divide your plane into 4 quadrants. Right?
Okay, yes.
Right. This is the x-axis, this is the y-axis, and this is called what? The abscissor. If I can spell this right. Is that right? Abscissor. Oh, I left out an S. There are 3 S's in this word. A-B-S-C-I-S-S-A. That's the abscissa, and this is the ordinate. Okay. But at this point, we're just talking pure math. Right? Numbers and pairs of numbers. Right? If I put a point anywhere on this graph, it is representing an X and a Y value. Right? We know that the X value would come out this far for the X distance, and then would go this high for the Y distance, and there's my number. There's my point. All the X's on this side are positive. All the X's on this side are negative. Y's on this side are positive, and Y's down here are negative. So you can have negative values in your system. As a practical matter, for most data sets that you'll get in the sciences, you'll stay in this quadrant right here, positive, positive. Occasionally, and we've got examples here that you're going to use to graph, you get maybe a negative, so you might come over this far. But usually, you stay in this one. All right. Let's see. I don't want to miss any points. We're using data. Now, data is plural. If you've got 2 or more numbers, you've got data. If you've got 1 number, you've got a datum. That's Latin. So when we say data, we're usually talking about numbers, but sometimes you can have data in a descriptive format. Right? And we're not going to go there. Most of the data I've ever seen has been numerical. Okay, so that's how you would position 1 point, this datum. If you had another one, right, it might be here. It would have a different X and a different Y. Right, that's 1, 1. And now to relate that to an experiment, because supposedly your data came from an experiment. If you have, typically, when you devise an experiment, you as the experimenter have control over one of the variables, which is the independent variable. Right? That's one you control. And that one is plotted relative to the x-axis. So this is the independent. And the response of the system that you're investigating, what does it spit back at you, is on the y-axis. This is the dependent. So for example, you've got one example in here. Let me see. We'll come back to that other stuff. This one has temperature versus volume of a gas. So if you have temperature plotted down here and volume here, if you change the temperature of a confined gas and you maintain the pressure at a constant level, you don't let the pressure increase, then what's happening is the volume will increase. Temperature increases, volume increases. And you can plot various numbers on here, and you could string them together with a best fit curve, best fit line. While we're here, since this is the independent and that's the dependent, the axis must have units of measure. So in that example there, the units of measure are K, right? Kelvin temperature. And the volume is, I think, in liters. Okay, so you have to identify the axis and the units of measure. And then you also have to say, where are the units of measure on that line? Okay. Right? Is it maybe 50 here? It may be 75. Well, that wouldn't be right. 50, 100, and then 50 more is 150, and you just keep going up. Now, for this example, right, K is always positive numbers, right, because it starts at absolute zero. You never go negative. So we're going to stay in this quadrant because of the physics of the matter. And then the volume changes here, and you need how many liters here, right, whatever the values are, and you identify them with numbers. Those sometimes we call the tick marks. Some major tick marks, and then you might have little ones in between the minor tick marks. And then one other thing you need in your graph, besides labeling the axis and positioning your data in points, and maybe drawing a best fit line, is a title. Every graph must have a title. It's something that describes what is in the graph. And sometimes we even go to the trouble of putting footnotes in to help explain it. But it's got to have a title. Right? Every graph must stand on its own two legs. If I pull this graph out from a paper and take it over to my desk to look at it, and I forget which paper it came from, the title will tell me what it's talking about. Okay, so those are the things you need when you draw your graph. Got to have a title. It's got to have axis labeled with units of measure, your tick marks, and your data. And we'll talk about how to fit that in the paper in just a minute. But let me back up. I skipped a bunch of stuff in here. Back. Okay, dependent, independent variables. Okay, there you go. The axis, quadrants. Let me, I didn't skip that much. Okay. This particular table has the data set right next to it. I think that's just for convenience. You don't have to. The next point I would make is, if you draw how do you draw a best fit curve for a data set? Well, if you've got several points here, right, like that, you want to draw a line that minimizes the distance between the line and your points. You want it to cover the region, but decrease the variance between the two. Once you've got that line drawn, then you can characterize the line. If it's a straight line, that's better, because all straight lines follow this pattern. Remember this? Right. There's the independent variable, the dependent variable, the slope for the line, and the y-intercept. And if you have that, then you have mathematically described that line. Now, that doesn't describe all the points, because maybe the points don't fall on that line, but this is the best fit line. Okay. All right. Say you draw the line, and you've got data points here up to here, in there somewhere. If you want to say something about what would happen if the temperature were at a given point, but it's not one of your data points, that's where the line comes in. Then if it's not in your data set, then you say, if I change the temperature to this value, I go up to that line, then I go across, and that's what the volume would be. Okay, and so I pick a number that's within the range for my independent variable and find out what the dependent would be. Or you can go the other direction. What temperature would it take to give me this volume? But if you work within the data set in here, that's called interpolation. And that's the safest region to be. I mean, if you're going to estimate something that's not in your data set, interpolation is the best place. But occasionally we have to go outside the data set. Right? So we extend the line this way and that way. So if you go outside the line to make these same types of inferences, this would be extrapolation. Okay. Statistically speaking, the best region to be in is in the middle of your data set. The worst region to be in is outside your data set. Because if we draw a supporting line on either side showing what's the range, right? Where could those points actually be, statistically speaking? Does anybody in here have statistics? Good, good. So our uncertainty range might look like this. Right? Outside your data set range, it really goes, right? It gets bad in a hurry. So you may interpret the line out here, but the number could be anywhere in there. Okay, statistically speaking. So extrapolation, we only use it if we have to. Now, it depends on the data set that you draw from statistically as to whether this is a big deviance or just a little deviance. Right? If you got a monster data set in here that's just, I mean, it lays right on the line, then it's probably pretty narrow extrapolated. So I'm going to leave that to your further study in college with statistics if you need to go there. I've had 2 statistics courses, one introductory and one experimental design. They were pretty fun, actually. The experimental design was taught by an animal scientist.
Interesting.
So he used as an example his study of cattle, and they would count the respiration rate as, you know, how they were bellowing. You could watch from a distance, depending on the air temperature and where they were located. And they did all sorts of correlations with it. Whatever it takes to get funding, right? Okay, so data points, straight lines. You can get curved lines also. So the next point is, what's the relationship between your independent and your dependent variable? Is it a direct relationship, which would be as one increases, the other increases also, right? So a positive slope, lower left to upper right, that's a positive slope, means it's a direct relationship between the independent and the dependent variable. As this one gets bigger, that one gets bigger, right? Come out here, right there, there. Come out here, yeah, oh, yeah, it's getting bigger. That's a direct relationship. If we had a negative slope, say our line went the other direction, right? Then as this one gets bigger, that one gets smaller. So the slope here would be a positive number, the slope here would be a negative number. And that would be an inverse relationship. Okay. Now, that's the example here I gave you was straight lines, right? Straight line, positive slope, straight line, negative slope. But you can have curves, right? And the one that's given as an example here, and one that you need to graph, is pressure versus volume. We change the pressure on the gas, the volume changes. So as the pressure increases, the volume decreases, right? Just makes sense. But it doesn't make a straight line. It goes like that. And that's not very, very dark, is it? There. That's a special kind of curve. Okay. Remember in math, the curve where the tails never touch the axes. Remember what that's called? I'm sorry? No. Parabola is like parabola is like that. This is a hyperbola. Hyperbola. So that's and writing an equation for this depends on the physical process that you're describing. In this case, we're describing the ratio of pressure times volume is equal to some constant value. we'll talk about that later. That's Boyle's law. But notice that if you have two variables times each other equal to a constant, then if this one goes up, that one's got to go down. Mathematically speaking, that's the only thing that can happen. But in a minute, I'll show you how to convert that into a straight line using the same data. Well, modified data. But let me get rid. Okay, direct relationship, inverse relationship. So the slope here changes, right? Nobody's had calculus in here, have you? Have you been introduced to the tangent to a line? Tangent. The tangent to a line is the straight line that touches the curve in only one place. Right? So we could draw a tangent here, a straight line tangent like that, but over here it would be more like that. Right? So the the straight line tangent is changing, so the slope is changing too. But in general, as we increase p, volume decreases. Right? That's still an inverse relationship. Okay. And these are things that you can use to discuss your data. Once you draw it and put it on a graph, then you can point out these things to your readers and relate them to some concept that you're trying to get across. Okay, so the next item in this discussion is preparing the graph. So how do we prepare the graph with a data set? Well, I don't have a good data set handy, so let's just assume we've got an X and a Y, right? And you've got data pairs like that. So if we set X at something, then Y is the response, and you get a set of numbers that you graph. Okay. How do you know if we're going to do this by hand, right? The first time, right? They're graphing programs, but it's always good to do it by hand one time. And then you can go to technology to help you the rest of the way. So how do you get that data on your paper so that it makes the most effect? Right? Well, a sheet of paper, like the ones that are in your lab, they come in, you can either put them like this, which is called portrait orientation, or you can turn it 90 degrees, landscape, yeah, right? And you've still got these the square grids there to work with, okay? So which way do you orient it? Well, the guiding principle is you want to use the space to the maximum possible, right? Spread your data out in that space so that it's easier to see differences and go back and interpolate or extrapolate if necessary. Okay, so that's one thing that you want to decide first is which way do you want to orient it, and that's based upon your data set. What's your range? Right? If your range is really big for the X, then it probably wants to be this way, and so you can spread it out like that. But if your range is bigger for the Y, maybe you want to go this way. Okay, or if you have negative numbers in there, right, you may want to move this Y-axis over here so that you'll have access to negatives here and positives there. Right? One of those exercises in here, you will need to do that. Temperature versus volume, because in that exercise, temperature is in degrees Celsius, which goes negative at some point. Right? And then when you draw your line, you can extrapolate down to the further down here. Okay, so orientation based upon range. Then you want to set the actual range on the axis to accommodate your data so that you can interpret it later. In other words, you've got these squares, and you'll notice that you've got major lines like this, and then in between you've got 5 lines. Right? If you look at your graph paper, it's one of them's heavy, and then you got the lighter ones in between. Those are like minor tick marks. So what you want to do is decide with your range, how can I go out here with the easiest way to read my data? In other words, if you've only got 5 lines here, then maybe you want to take 2 of those together as the difference between this value and the next value. Then you can read it as tenths. Right? Think in decimal terms. And then you say, okay, if I say my data set is like up to 100, then I'm going to need 10 of these groups or 20 of the dark lines to get from one side to the other. See if you've got enough room for that. If you don't, you might have to shrink it down. But what you don't want to do is shrink it down so that your line is maybe like this. That doesn't tell you or your reader anything. Right? And students do that. They paint themselves into a corner by setting the values like each little square is 1, 2, 3, 4, 5 on their data set, and that's as far as their data set goes. So they're stuck. They're down in that little corner, right? And that looks horrible. And in the real world, it could cost you your job. If you don't know what you're doing and can't convince your boss that what you're doing is worth it, say, all right, hit the bricks. So there are real world implications to learning how to do this stuff. If you want to be in the sciences. I mean, if you don't, then the other things you could do, like politics or legal profession, and you could just fake it all the way through. Okay, so let's see, what do I need to do next? Then once you've decided how far you're going with your data here, then you want to label your axes. You want to set the axes far enough from the edge of the paper so you got room to write your numbers and labels in. Label the axis, put in your tick marks and write in what they represent. You don't have to write every little square has a value. You just want to set it up so that you can label, and then the minor tick marks would be in between those. Okay. And once you got that set up, don't forget the title. Label with what's the axis, what variable is the axis, and what are its units of measure. And then you can start putting your data in there. Start plotting your data, and then you want to draw a best fit line. Hopefully it'll be a straight line, but if it's not, do your best to draw a best fit curve. One device that you can use if it's not a straight line is a French curve. Has anybody ever seen a French curve? They usually make them out of plastic now, clear plastic, so you can see your data points underneath the curve. And it's a curve with a decreasing radius. Right? Starts out with a gentle slope like this, and then it just goes like that. So you got various radii built into this curve, and you can just position your curve depending on whether you need a tight fit or a broad fit, and that will help you draw a best fit curve for a section of the curve, and then maybe the curve changes more and more, and you can just keep moving it until you get something that fits with the least deviation. That's how we do it manually. Right? With computer programs, and usually you can call up an algorithm of some kind that'll make it look nice. That's what you do if you're going to publish in a referee journal. But for now, we're just going to do it the hard way. Okay, let's see. Okay, we've done that. Interpolating a line. We've done that. Extrapolating, interpolating, calculating the slope. Remember how to calculate the slope of a line? We're sticking with straight lines now. What's the slope of a straight line? Rise over run, exactly right. So let me clean this out a little bit. So there's the line that we drew to fit our data, right there. And if we take rise change in y divided by a change in x. That's rise over run. So what do you need to do the delta y? Well, you need to be on this axis, right? And you're going to have from this point right here, this point right here. So it'd be this one minus that one would be delta y. And then delta x would be this one minus that one, those values. That would be, in the quotient of those two would be your slope. And that would fit into your equation right here, m. Okay. Now, it'd be nice if when you draw your line, two of the data points, well, like here and here, say those two data points actually fall on your line and they came from your data set. Then you could just use the values. You wouldn't have to read it off the line. But if you've got a best fit line and none of your data points fall on the line, then you just have to pick two. Right? Pick one here and here on the line and read their values and then do the calculation. Right? Either way works. So that's the slope of the line. Now, we've got a value in here. So we can say y equals some number m times x. How do we get b? The y-intercept. Where the y-intercept is where x is equal to 0. Right here, 0. It's going to intercept the y-axis. Well, this one shows the origin, but it doesn't always happen that way. So in order to do that, if you've already got the slope calculated, put the value of your slope in there, then find two data points, x and y, that fall on the line. And again, if that point is in your data set, so much the better. But pick one in the middle, because we know that the deviation in the middle of your data set is probably the least. Or if it doesn't, then find a point in some point on the line and then read off the x and the y and plug those values in, x and y and m. Now you've got an equation in one unknown. You can solve for the b. Okay. Then when you write your equation, you would say y is still your unknown, and then you have a value for m, x, plus a value for b, and that would be the expression of that straight line, mathematical expression. Or if you know what these are, you could say, all right, so it's going to be v volume equals whatever m is times temperature plus whatever b is. We could do that either way. It's fine. For our purposes. Right? If you're publishing it, then you want to go this route because that fixes it to this equation. And sometimes when the data is plotted using a computer program, it will spit out the equation for your straight line for you. It'll also give you some other statistical values. Remember the R-square value? Goodness of fit? No, didn't get that far? Okay, that's okay. All right, so let's see, where are we at? We got the slope, and let's see. Oh, okay. Nonlinear relationships. All right. Here, this example is the one where I showed you with pressure volume with the nonlinear. So how do we convert that particular relationship into a straight line so that we can determine the slope? Straight lines are much more well-behaved than curves are. Sometimes you can't get away from curves, but when you can make a straight line, so much the better. Let's see. So we have our data set of pressure and volume. Let's see. Pressure, let's see, we change the pressure and get the volume. So pressure is X, volume is Y, and we got these values here. And actually, you've got an example there on that page, this data set right down here. And it's got pressure in atmospheres and volume in, I'll just write those in. This is in atmospheres and this is in liters. And it's got another one over here. All right. Why and how did we get that right-hand column? Notice what it says. It says 1 over V. Anybody know about reciprocals? Reciprocal is just the number moved into the denominator and divided into 1. That's the reciprocal of this value. Okay?
So it's like the opposite base.
No, opposite would be change of sign. Right. This is a reciprocal. So remember, whatever we do to a variable, we do to the unit of measure also. So the unit of measure for this would be liters to the -1. Right. Remember, -1 is the same as inverting the number. Okay. Now, why did we want to do that? Well, look at this. Remember that equation I gave you? Pressure times volume equals a constant. Okay. Let's do some mathematical wizardry here without breaking any rules, of course. One rule is if we do the same thing to both sides, then that's permitted. Right. Suppose I divide both sides by V. I just take that variable and divide this one by V and divide this one by V. Right. That's permitted, correct? Okay. Notice that this one cancels out, right? V divided by V is 1. So we're left with pressure on this side. And on this side, we've got K divided by V. Well, we can factor that out too, can't we? K's in the numerator. 1 over V then would be factored out times K. Is that correct? Isn't that right? You can take my word for it. Okay. Right. We just factored the 1 out over V times it. Well, prove it to yourself. What is K times 1 over V? Right. Numerator, numerator. K times 1 is K. So it's K over V, right? So I'm not fooling you. I mean, that's true. Okay. So if we've got P equals 1 over V times K, that's starting to look like a straight line, right? Actually, let's change it around. Let's put the K in front times 1 over V. There we go. That's better. Well, we can do that. So this looks like Y equals M, and this is X. So what's B? B is 0. B is 0. So this K value is the slope of the line. If we plot P against 1 over V. Now they put P on the X. Yeah, that's right. The way this is written, it says P is Y, right? The dependent variable, but it's not. This is still the dependent variable. It just turned out that way. And if we plot this, then you get that second line. If you plot pressure against 1 over V, this one against that one, then you get a straight line. And we can deal with that. Okay? So let's say we plot that and we get this straight line with let's do it the way they did it. 1 over V over here, 1 over V. We got P over here. We got a straight line that goes through the origin like that. Okay. Let's say our data set really doesn't go down that far. Maybe it goes up like that. And this would be an extrapolation. Okay. So if we want to do some interpolating, right? We want to find out at what pressure would the volume be, say, 40 atmospheres. If we had 40 atmospheres here, what would that be? 1 divided by 40? 1/4 is 0.25. 1 over 40 is 0.025. reciprocal meters. You can check me out on your calculator. I think it's right. All right. So if we say that we have plotted values here that are not 40, but they're 1/v, right? And you can see them there. They're fractions. They're small fractions. So that's what happens when you divide a big number into 1. You get small numbers. Okay. So we know now that off this graph, what we want to do is look for 0.025, right? And I don't know where it is. Maybe it's right here. We follow it over here. That's the pressure. We don't look for 40 because 40 is not plotted. The inverse of 40 is plotted. So then we go to look for the inverse of 40, and then we can find out what the pressure is. Okay? Did I lose you? Okay. So that's called data transformation. Now, the rest of this discussion introduces concepts that are good, but they're not essential. In fact, beyond this point, these concepts I put in the back part of the exercise in bonus section. So you can do them, answer those questions, draw those graphs if you want, and get some extra points. But the required section stops at Boyle's law, P times V. So if we go down here and look, see there's another different. This is this is what's called a sigmoid curve, right? It looks like an S. Okay, you see that in this acid-base titration, looks like that. You see it in growth curves, right? If anybody a biology major in here, you see it in growth curves and numbers of a population over time, right? You'll see it. Let's see. Over time, the numbers in a population, they'll start off slow, right? And then they get into an exponential phase, right? When they double and double and double and double, and then the doubling really starts to kick off like that. And then what they do is they start exhausting their resources, right? And then they flatten out. So you get a sigmoid curve for growth of particularly microbial populations. Right? It's easiest to see it there. Or something with a short lifespan, like fruit flies. Anyway, in this case, it's a titration curve. And the equivalence point here is a point at which the amount of acid equals the amount of base. Right. So we're going to use that. I don't know if we use that in this class or not. I know we're going to get to it. Titration? I don't think we have time. I'm sorry. It would come at the very end. If we can squeeze one in, then okay. But I don't know if you noticed, but the last couple of semesters, they chopped a whole week out of the end. Just it's gone. I used to have 15 weeks of work. Now I've only got 14. Now, I'm sure on paper, they're satisfying the Higher Learning Commission for their certification. But as a practical matter in class, they just chopped out a whole week of study for me in my class. And that's where that titration went. It would be fun. What I could do, I guess, is maybe just chop out one of the other labs and stick it in. Yeah, but I haven't set it up for that yet, because the other labs are equally important. Okay, so here's the required section, and it's worth 78 points. And then there's a bonus section worth 39 points. So the first part of it is just regurgitation. I mean, what do these terms mean? Let's see. I will make a point. So here are 5 items you have to consider when you're putting your data on paper. That's what that question's about. Number 3. Number 4 is, what does a data point on a graph represent? We've been talking all around data and what to do with it, but where did it come from? Right. I'm sorry, measurement. Yeah. Yeah. Each one of those data points represents a measurement. Okay. Well, let's take that ball and run with it. How should we not expect all data points to fall on the straight line? Should we expect them to fall on the straight line? You know, if they're right, if they're this type of data set, should they fall on the straight line? Why not? Yes, one word, uncertainty. Every measurement has built-in uncertainty. Process for drawing a straight line, I covered that with you. And then some of these questions are like, if I give you this experiment, which one is the one I control, the independent variable, and which one is the response, the dependent variable? Okay. And then draw the graphs. And then for this one, you're doing a calculation of first, actually, that this one right here, yeah, that one right there, I would leave that one until I determined the slope of the line and the line itself down here. You got any idea why I would do that? I'm sorry? Well, yeah, ultimately. But no. Well, you could answer parentheses 4 and 5 from the graph itself. You know, just read it off. Or you could go down and calculate the slope and get the y-intercept and get the equation for the line. And then when it says, what would the volume of helium be at 5 degrees C? Plug in 5 degrees and calculate it. Okay. That would be the easiest way, I would think. And you can do the same thing for 5, right? If it has a volume of 4.20 liters, what would be the temperature? And remember, when you write these values in, they all have units of measure. Right? So be sure and put the units of measure in. It's worth points. How about the slope of a line? That one might give you a little trouble. What would be the units of measure for the slope of a line if we plotted temperature against volume? Isn't that this one, temperature against volume? Yeah. Temperature against volume. This will be degrees C, though. So the slope of the line would be a change in volume, which would be liters, and a change in temperature, which in this case would be degrees C. Right? So if you divide that one by that one, your units would be, right? You do the same thing to units that you do to the numbers. If you divide the numbers, you divide their units. So the units of measure would be that compound unit. Okay. Let's see. It's just a little after 12. There's pressure volume, right? Right, we drew that hyperbola. So that has 2 graphs with it. The one on the previous page had 1 graph, temperature volume. This one has 2. The first one is just the raw data. It's going to give you the curve, pressure volume. The second one is going to be that transformation where you do the reciprocal of volume. And that's what the question down here for use the technique described in this experiment to express the data in a different way, one that will result in a linear relationship between the variables. Right. So to answer that question, you just tell me that you're going to take the reciprocal of the volume and do it. Okay, that answers that question. And then parentheses 5 is one where you plot that data, pressure against 1 over V. And that gives you a graph with a straight line. And then down here, that must have been where I got the 40 liters. It was subliminal. I thought I picked it out of thin air, but it was suggested to me by reading this lab. Right, so how would you use that to find the value with your straight line graph? You would convert the liters like you did all your other data to 1 over V, right? 1 divided by 40, and then read that off of your graph. And there's the bonus section, right? So you're welcome to do that if you want. I would just emphasize that the first one is going to be that titration curve. It's going to look like that, sigmoid. The second one is what's called a broken curve. It's got, let's see, here, this data. It's got part of the curve is going to be down here, and the rest of it's going to be up here. And there's an example of that in the discussion too, to help you if you want to do it. It's worth some points. Okay. Now you can fill out. This is the form, and you can do it on the hard copy, right? That's fine. Turn it in. That's great. Just turn in the hard copy. But if you find yourself in a situation where you can't come next week, then you'll miss that lab. Plus, you need to turn in this lab. That's the pattern. When we walk in here to do a lab, then the one we did the last time is due. Sometimes it's every week, and sometimes we skip a week. And like when it comes to Thanksgiving, we're probably going to skip 3 weeks. Any questions? No? Well, we're done a little early. If you don't have questions, if you want to sit down and try to draw some stuff and let me critique it, that's fine. Otherwise, you're free to go till next week. Don't forget your lab equipment though when you come. Bring everything you're going to need for safe performance. And at that time, we'll distribute the buckets. Right. So think about who you want to be your lab partner. I think we've got 7 buckets. Right. So that's enough for we can have 2 per group. I've had 3 per group if you prefer. That's okay. I don't want 4 per group because then one person does it all and 3 people do nothing. So 2 is actually better. Huh? Yeah. Also, if you happen to miss a lab 1 week, then you got to depend on your lab partner to get you the data so that you can complete the report. Otherwise, you're kind of out in left field.